Now let's look at a slightly more complicated example, that of the expected number of inversions in a sequence of keys to be sorted. Suppose we have an array A from 1 to n of n distinct numbers. We can actually generalize this to non-distinct numbers, but the analysis is much easier if we assume distinct numbers. An inversion is when essentially two items are out of order. If I is less than j, but a sub I is greater than a sub j. This obviously has important applications to sorting. Suppose we want an array sorted in increasing order, then an inversion is a situation where two items are out of order, so they need to be changed. We usually measure the time complexity of sorting algorithms in terms of the number of comparisons that have to be made. And in some sorting algorithms, the number of inversions is directly related to the number of comparisons that have to be made. An example is our familiar insertion sort, because when you're moving your way down an array, you've got a number you're trying to insert into the already sorted sequence. As you move that number down the array, you have to compare it to all of the one more than the number of items that are inverted. You keep comparing until you get to the point where you no longer have to move it down. So the number of inversions controls the number of comparisons that are required. There are other sorting algorithms that are able to sort without doing a comparison for every inversion, and we're going to learn about them later. But an inversion, the number of inversions in input data gives us an idea of how unsorted some data is. So for example, let's get concrete here, look at some examples. Suppose we have the best case, we have some numbers in the array, and they're in sorted order. What's the number of inversions? Well, 0. Every time j is greater than I, then a sub j is greater than a sub I. So there's 0 inversions. Now let's look at the worst case. How many inversions do we have here? Well, here's one inversion. 9 and 10 should be switched. So there's one of them. Here's two more inversions. 8 and 9 should be switched. 8 and 10 should be switched. There's two of them. Here's 3 more. And so on. So as you can see, since we started here, if instead of 10 I write n, we're going to have, well, I'm going to have to add it up here. We're going to have 1 plus 2 plus n minus 1 inversions. Well, how many is that? Well, we know that we have the general formula. Remember the story I told you about Euler, who was asked to add up the first 100 numbers and did it in a few seconds, and this was a formula he used. That's the sum of the first n numbers. Here we're doing the sum of the first n minus 1 numbers, so instead of n we got to write n minus 1. So we're going to have n minus 1 times n minus 1 plus 1, which is n over 2. So we're going to have n squared minus n over 2 inversions in the worst case. So what about in between? What about the average or typical case? You know, if we got 3, 1, 7, 2, 4, 8, how many inversions are there in a typical case? You know, here we might see, you know, for example, that this is an inversion, and this is an inversion, and that's an inversion, and so on. How do we count that up? I mean, that's really complicated. So the wrong way to do this would be to say, for a permutation, such as this is a permutation of n numbers, right? For any given permutation, the hard way to count this would to be asked, what is the probability of k inversions? That would be really hard to count. That's like asking what's the probability of k heads in the coin flip thing. And so in the coin flip thing, we wanted to recast the problem so we could ask a very simple probability. Each flip, the probability of a head is 1/2. And we're going to do a very similar strategy here. If we didn't do it, how many problems, how many things would we be dealing with here? Well, how many permutations of n numbers are there? For the first position, we can choose any of the n numbers. For the second position, we can choose any of the n minus 1 remaining. For the third, n minus 2. And this is a product because for each of those, you could choose any one of those, any one of those. So there's actually n factorial permutations, which is more than exponential. That's a large number of cases to have to reason over and to think about, well, how many inversions is there in each of those cases? So that's the hard way to do it. Let's now think of the easy way to do it. So if it's really hard to count the number of inversions in permutations and the probability of a certain number of inversions being in a permutation, let's just count the number of inversions directly without worrying about what permutations they're in. So we're going to define an indicator random variable as follows. It's an indicator random variable for the event where a sub I, this is the inversion, is greater than a sub j. So what this says is xij, with I and j ranging from 1 to n under this constraint where j is greater than I, then it will have the value 1 when there is an inversion. So the value of this variable will be the count of the number of inversions. Okay. But we know that the probability that this random variable takes on a value 1 is 1/2 for any given xij, because for any given xij, you're just dealing with two numbers, and chosen randomly, either the first is bigger or the second is bigger. So we've just turned a very difficult probability estimation into a very simple one, just dealing with two numbers at a time, not caring where they are in the permutation. And this makes everything very easy to count, because by the lemma 1, remember that lemma 1, we're going to use the fact that the expected value of xij is, of course, also 1/2, because the expected value by lemma 1 is the probability. So let's do the math now. So we want to find our x is going to be, I'm going to leave a little space here. I'm going to let I run from 1 to n minus 1, because j is going to run to n. So these are the pairs of positions in the array being considered. But j has to start bigger than I. So essentially this expression says for all possible combinations of I and j that meet the constraint that I is less than j and they're within the range of the array, add up whether those two are out of order. So any value of I and j, x of ij will either be 0 or 1. And so the total number of inversions in the array, this x over here that we're interested in, is going to be the sum of whether or not each pair of variables in the array is inverted. Very simple. Now, to find the expected number of this, to actually do the math, we just take the expected value of both sides. And now we just do the same pattern I showed you in that very simple proof before. Using linearity of expectation, we can now move that e inside. So let me write this out carefully. Same summations, but we've now moved the e inside, because the expectation of the sum is the same as the sum of the expectation. But voila, we already have a number for that. We can now get rid of that pesky e. I guess I'll try it here and see if I can. Okay, same expression, 1/2. Okay, very simple. Now, but we got to get rid of this nested summation. To do this, we're going to use the fact that this is actually equal to n choose k. Sorry, n choose 2. This nested summation is essentially just ranging over all possible ways to choose 2 items out of n. So there's going to be n choose 2 times that we add up 1/2. So it's equal to n choose 2 1/2. Well, what is n choose 2? Your textbook has very useful formulas in the back. There's formula C2, which says that n choose k is equal to n factorial k factorial n minus k factorial. But in our case, k is 2 factorial n minus 2. So that's what we really have here. So that is equal to n. Now notice n minus 2 factorial is n minus 2, n minus 3, n minus 4, and n factorial is n minus 1, n minus 2. So n minus 1 are the only ones that are left. So this top expression is n times n minus 1. And of course 2 factorial is 2. So we've canceled out, essentially we've canceled out this term and the tail end of that term, leaving this here. So that means that this is equal to n minus 1 over 2 times 1/2, which is equal to n minus 1 over 4, falling off the bottom of the screen there. So I'm going to write over here the final result, simplifying that further, so that's n squared minus n over 4 is the expected value of the number of inversions in a random array of numbers. Now remember, when we did the best case, it was 0. When we did the worst case, it was n squared, sorry, that's n there, yeah. In the worst case, it was n squared minus n over 2, which is order of n squared. And here the expected case is divided by 4, so there's half as many, but it's still, because of this largest growing term, it's still order of n squared. So the expected number of inversions is going to be order of n squared, although strictly less than the worst case. So hopefully you see and appreciate how much simpler it is to do probabilistic analysis using indicator random variables and following this general strategy where when faced with a complex distribution of probabilities, we think of a way to break up the problem into pieces where we can come up with an indicator random variable that has a simple probability that we know, and then we write in an expression that takes the big X we're looking for, breaks it up into those pieces. We use linearity of expectation to move the E inwards so that we now have we're asking for the expectation of the piece, not the expectation of the whole thing. That turns out to be something that we already know the answer to. We can replace it with that answer. And then we might have to do some algebraic simplification like we did here using combinatorics, which I would emphasize, this stuff you really have to be familiar with in this course. And I don't remember all of these formulas. I'm always looking them up, but just be comfortable, at least able to find ways to solve these things. So that concludes our example of the expected number of inversions using indicator random variables. And next we're going to move on to randomized algorithms.